Hi everyone, we are going to continue with some chapter 4 problems, and here's another static equilibrium situation. A heavy weight is suspended by actually 3 cords as illustrated below. Determine the tension in each of the 3 cords. We have T1, T2, and T3. So let's take a look at these. T1 we don't know, T2 we don't know, and T3 we don't know. Now T3 is supporting all of the weight below it. And this is, if you refer back to my lectures, this is like the dead fish scenario. All of the weight is suspended by one cord. It's not moving. So the tension in T3 is 3,000 newtons. That we can answer right away. That's a pretty simple situation. But T1 and T2 are pulling off up to the right and up to the left. So what we're going to have to do with those two tensions is we're going to have to break those into vector components. And then we're going to have to sum the forces in a vertical direction, and we're going to have to sum the forces in a horizontal direction. And because this is a static situation, nothing is moving, those are going to equal 0. So let's go about and do that. The sum of the forces horizontally are going to equal 0, and the sum of the forces vertically are going to equal 0. And let's break those two vectors into vertical and horizontal components. I'm going to see if can I make this bigger? I cannot without making a mess. Okay, I'm not going to do that. Here goes nothing. Now this vector is up until the left, and I'm just going to make these vectors a little bit bigger. Why? Because I want more room to write. That's why. So T2 is pulling up and to the right. And that vector has two components to it. It has a horizontal component and it has a vertical component. And remember, I'm just drawing this picture extra big so I can illustrate some things here. Now, alternate interior angles. If this is 71 degrees, this is 71 degrees. The hypotenuse of this triangle happens to be T2. On the other side, this is, I'm going to make this triangle out of a different color. This T1, we're going to make again, we're going to make this kind of big. This is going to be T1. And alternate interior angles, if that is 26 degrees, this is going to be 26 degrees. And what's going to happen is the up vectors are going to equal the down vector. And so let's do what we've done in the past. Here's an up vector, here's an up vector, and those two are going to counteract my down vector. Those are going to be my forces in my up and down or my y direction. My forces in the horizontal direction, the pull to the right is going to counteract the pull to the left, and those are going to be my x forces. Now we're going to have to put some numbers on these. So let's go ahead and build some of these equations. So in the x direction, first off, to the left, this is going to be T1, my hypotenuse, T1, times the cosine, because this is an adjacent side, cosine of 26 degrees, that's my pull to the left, is going to be equal to the pull to the right, which is going to be T2, this hypotenuse, times the cosine of 71 degrees. So my pull to the left is going to be equal to my pull to the right. That's my sum of the forces horizontally. Let's look at my forces vertically. My two ups are going to equal my downs. So let's look at this up on this side. This is going to be my hypotenuse, and I'm going to change colors so we just keep our equation straight. T1, this is the opposite side, so times the sine of 26 degrees, plus my other up force, which is going to be this one, T2 times the sine of 71 degrees. Those two up forces are going to equal my down force. What's my down force? The weight of the block, 3,000 newtons. Now, I now have my mathematics good enough that I can do it. I have two equations, two unknowns. I don't know T1 or T2, T1 or T2. And what I can do is solve one of these equations for one of the unknowns and then shove it into the other equation. Now it's a matter of algebra. What I'm going to do is I am going to solve this equation for T1. Would it matter if I solved it for T1 or T2? It would not. I choose T1. Why? Because I want to. That's as good a reason as any other. So T1 is going to be equal to T2 times the cosine of 71 divided by the cosine of 26. Now, if carrying these sines and cosines with you is kind of a pill, you are allowed to change these into decimals, but always carry them out to 4 decimal places. So I'm going to go ahead and do that because I think that's a little bit more comfortable. So if I do cosine of 71 divided by cosine of 26, I end up with T1 equals T2 times 0.3622. Now remember, if you take a cosine or a sine and you transform it into a decimal number, always carry it out at least 4 decimal places. Now this is what T1 is equivalent to. So I'm going to replace T1 in this equation with this. And then the only thing in that equation will be nothing but T2. So let's go ahead and do that. So I now have T2 times 0.3622 times the sine of 26 plus T2 times the sine of 71 equals 3,000 newtons. Let's get these transformed into some numbers. So the sine of 26 times 0.3622. So this ends up being T2 times 0.1588 plus T2 71 sine of 71 gives me 0.9455. If I add those together, I end up with T2 times 1.1043 equals 3,000 newtons. To solve for T2, I get 3,000 newtons divided by 1.1043. 3,000 divided by 1.1043, and I end up with T2 being equivalent to 27, rounding it off to 3 sig figs, which is probably where I should have been all along, 2720 newtons for T2. Not too bad. All right, let's solve for T1. Now that I have a value for T2, I'm going to plug that back hither. So T1 will be 2720 newtons times 0.3622 times 0.3622. And I get T1 having a value of just 984 newtons. Does that sound about right? Okay. Now, if you are off like down here in about the 4th decimal someplace, it's a sig fig thing, not to worry. All right, we will see you later. Bye-bye.